Hello, everybody. Can you hear me?
We can.
Good, thank you.
Photo kids in class.
Okay, let's continue with what we were looking at the other day. All right, so I'd like you to mute yourselves, please, especially if you've got some background noise going on. Some of you do. Thank you. Okay, so we were discussing NMR. I had talked about the three things that make up an NMR spectrum. I talked about chemical shift, and chemical shift allows us to be able to tell what kind of hydrogen we're dealing with. I talked about integration, which is these numbers above the peaks, which tells us how many hydrogens we're dealing with. And then I talked about multiplicity, which accounts for the multiple number of peaks here that each peak is made up of, which tells you how many hydrogens are on adjacent carbon atoms. All right. So that's what we had talked about on Monday. Now, what I was going to do was go through how to solve a specific NMR problem. So the first thing you would do is look at the double bond equivalents, and we talked about that. That was the last thing I talked about before we finished here. And then the pieces that we can see based upon the integration. So what we do is we look at the numbers above these peaks, and we can usually get an idea of the pieces that we're seeing by looking at the integration. So 2H is CH2, 3H is CH3, 2H is CH2, and 3H is CH3. So those are the pieces that we can see. The next thing we need to do, and this is a very important step, is we need to figure out what we can't see by subtracting the pieces from the molecular formula. So when we look at the math we have to do for that, we've got C5H10O. Remember, we do have the molecular formula, and we subtract out. So somebody's got. I'd really like you to mute, please. Somebody needs to mute. Thank you. Then we subtract out all of the pieces that we can see. What we're left with here would be a C, an O, and a double bond equivalent. You'll notice that the double bond equivalent isn't part of the pieces we see, so it must be part of the pieces we don't see. So what we've got left is a C, an O, and a double bond equivalent, which would be a C double bond O that we're not seeing. Now, the important reason for why we're not seeing the C double bond O in the spectrum, why it doesn't come up in the spectrum, is because it doesn't have any hydrogens on it. So a C double bond O is completely bonded and has no hydrogens. That's why we don't see it in the proton spectrum. The only way that we know it exists is because we've been able to subtract out the pieces we can see from the entire molecular formula and infer its existence as a C, an O, and a double bond, making up a C double bond O. So we know that the structure then is made up of everything we can see and everything we can't see. You'll notice that when I've stated these pieces, I've put these lines on, and these lines represent join points. So what I'm saying here is a carbon has 4 bonds on it. If 2 of them are hydrogen, then that leaves 2 other spaces for the carbon to bond. A CH3 has 3 hydrogens on it, so there's 1 space to bond. A C double bond O has 2 spaces left to bond. So that's where those lines come from. Does anybody have any questions so far? When we put this together, there's really only two possible ways we can do that. We can put them together so that it goes CH3, CH2, CH2, C double bond O, and the CH3, or we can put C double bond O in the middle. But we can already tell based on this spectrum that we have 4 peaks, which means there's 4 different kinds of hydrogens. Whereas this kind of arrangement where you've got the C double bond O in the middle would only have 2 possible peaks, A and B, and that's it. So I know that this would be the correct structure. At the end, you can check the multiplicities and make sure that those make sense as well. So let's see if we can do that. Here we go. Let me enlarge this a little bit. There we go. So what we can do is we can actually assign each hydrogen here, each kind of hydrogen, one of these peaks, because each peak is for one of those hydrogens. And the way that we can do that is by using a combination of 2 things, the multiplicities and the integration. So the 3H is going to be the CH3. So this CH3 and this CH3 are going to be A and D automatically, but we don't know which is which initially. But what I can do is I can say, well, this CH3 is next to 0 hydrogens. So that's why it's 1 peak. So if you remember the rule I had earlier from the multiplicities, I'll just write it here. So N peaks, N minus 1 hydrogens on adjacent carbons. So what I'm saying here is that we have 1 peak. That means there must be 0 adjacent hydrogens on carbon, and that would be the case for D. That's why D has been assigned a single peak. If you look at A, that's a CH3 as well. You can see that because of the 3H. And it has 3 peaks, which would mean 2 adjacent hydrogens, 3 peaks, 2 adjacent hydrogens on carbon. And you can see we've got a CH2 next to it. So that tracks as well. B and C are both CH2s. If you look at C, that CH2 has 2 adjacent hydrogens. So that would be that one there with the 3 peaks. And this CH2 has 5 adjacent hydrogens. 3 plus 2 is 5, which is why this one has 6 peaks. So that's how we can use the multiplicities to do that as well. Does anybody have any questions so far? Okay. Okay. All right, let me give you one other thing that's important here about multiplicities. If you look at the spectrum for this compound, it's going to look like this. And this will be about, say, 4 ppm. This will be about 1 ppm. This will be a 2H. This will be 3H. And this will be 1H. So if we look at the CH3, you can see that the CH3 here, which is the 3H, is next to a CH2. So we expect it to have 3 peaks, which it does. Remember, N peaks, N minus 1 hydrogens on adjacent carbons. So there's 2 hydrogens on the carbon adjacent to the 3H. Now, if we look at the CH2, you'll notice it's 4 peaks, and that's because it's next to the CH3. You'll also notice that it is also next to an OH, but the rule that I'm talking about here is hydrogens on adjacent carbon atoms. So if it's not a carbon atom, it doesn't count. The thing is, the CH2 sees the CH3, but it doesn't see the OH. So it's almost like this O creates like a wall, and the CH2 can't see the H on the O, and the H can't see the CH2 either, which is why it comes up as a single peak. So if it's an NH or an NH or an OH, NH, OH, or an NH2, then it will usually turn up as a single peak. It won't see the hydrogens on adjacent carbons because it doesn't count when we're talking about things that aren't carbon atoms. So that's going to matter as well. Does anybody have any questions? Anybody have any questions? Okay. Let's see. Let's go on to some resources that we have here for learning about this stuff. And it truly is all about practice. And, well, maybe, and I'll also go through a couple of test questions as well that relate to this. So let's look at let's look at a test question first, and then we'll look at how to practice for it. Oh, don't do this to me. All right. It's not going to let me access it. I'm on a different profile, and I'm not going to be bothered with it right now. That's very annoying. Let's look at we'll look at the answer key instead. We'll go from there. Now, the problem that you'll get on the test that relates to this will be a problem that actually consists of 3 spectra. There'll be a proton NMR, which is what we've just been looking at. There'll be a carbon NMR, which we haven't discussed yet, and an infrared spectrum as well. And I've got some notes about that. I'm not really going to talk about it very much in class. You'll have to, I want you to be on your own with that. I do have resources for that. You can watch the videos. But that's not going to be incredibly helpful to you anyway with this structure. It'll be a little bit helpful, especially if you know something about it. But if you don't, it's not going to harm you when you're looking for a structure here. So I'm not really going to be talking that much about the infrared, but I will point you to some resources to help you with it. It's mainly the proton and the carbon NMR that will be most helpful to you. So if we look at the proton NMR here, and the first thing we would do, we've got C13. I'm not going to worry about using the carbon to get this actually. We'll just do the proton. C13, H18, O2. And what we want to do is figure out what it would be once we accounted for the oxygen. It'd be C13, H18. If it were saturated, it'd be C13, H28. And that becomes from 13 times 2 plus 2. I'll write that again. That's where the 28 comes from. It would be, well, it's actually 28 minus 18 divided by 2. which is going to be 5 double bond equivalents. Yeah, 5 double bond equivalents. So what that would tell us is that it has a ring, aromatic ring, and that takes up 4 double bond equivalents. And that would mean we've got an aromatic ring and then one other double bond in the compound. So that's the immediate information that we can pick up with that. So what I had told you earlier is that anytime you've got 4 or more double bond equivalents, then you can definitely say you've got an aromatic ring. And if it's 5, then it'd be aromatic ring and then 1 more double bond equivalent. Now keep in mind that the reason it's 4 is because we've got 1, 2, 3 double bonds and the ring makes 4. So that comes out to be 4 double bond equivalents. So what we would do is the next step would be to figure out what we can see and subtract that out from the molecular formula. So I see over here in the aromatic region the C6H5. So that's an aromatic ring with 5 hydrogens on it. And then down here we've got 1H, so that's going to be a CH. It's multiple peaks, so it can't definitely be an OH. And then we've got a 3H over here, that's going to be a CH3. And then we've got a 9H, that must be 3 CH3s. So those are all the pieces that we can see in the spectrum. That's everything we can see. And now we've got to figure out what would be left over if we subtract out everything that we can see with this. Let me get my pad organized here a bit. It's not really behaving the way it should. So if you've got 6, 7, 8, 9, 10, 11, then we've got a C, we've got 2 C's left over. And the hydrogens will always work out because you see all the hydrogens. So the oxygens, we've got 2 oxygens left as well as 1 double bond, because this makes up 4 double bond equivalents for the C6H5. And when I say C6H5, I'm talking about an aromatic ring with 5 hydrogens on it, because it says 5H over here, which means that there's only 1 space left for something to join on. So we've got a C double bond O because we have a leftover double bond equivalent. I'd really like people, rather than, if you can possibly say something, I'd really prefer that rather than typing in the chat box. Is that okay, Millie? Can you talk or not? Millie, can you talk or not?
Sorry. Yeah.
Okay, yeah, I'd prefer you talk. It's much easier. So does anybody have any questions about how I know there's a C double bond O?
Yes, can you explain it one more time?
Okay, so you've got 5 double bond equivalents. You're okay with that, Mary?
Yes,
And you know that the aromatic ring takes up 4?
right.
That means we have 1 double bond left over. We have, this contains 5 double bond equivalents. And the C6H5, or the aromatic ring, contains 4, which means we have 1 left over. So we have 2 C's, 2 O's, and a double bond. And what I'm saying is that C double bond O is there because that accounts for the other double bond equivalent.
Okay. And how did you assign the 4 double bond equivalents for that? So you just said the whole thing would be a aromatic ring.
Yeah, well, what I said was that when I was talking about units of unsaturation on Tuesday, I talked about if there's 4 or more, then you automatically know that you must contain an aromatic ring.
Right.
And the other thing is that since there's 5 hydrogens on this aromatic ring, because you can see that from the 5H, it's an aromatic ring with one thing attached to it, which means there's 5 hydrogens around here. And that would be 1, 2, 3 double bonds, and the ring makes 4.
Okay, so you're saying the C2H5.
It's not C2H5, it's C6H5. Because this has 6 carbons.
Oh, so the resonance with 5H is C6H5.
Yeah, that's right.
Okay, and that counts for 4 double bond. We need to have 5, so the one more would be the CO. Okay, now I understand it. Thank you.
So those are all the pieces that we have. And I can also put some join points on here. So that carbon has 4, the C double bond O and the O here. Now the reason we don't see these in the spectrum is because they don't have hydrogens on them. That's why they're here. So the pieces that we have left, I'm going to erase all this over here. So now the pieces we have here and the pieces we have left are going to make up the structure of the compound. So this is where the challenge lies, and that's putting this all together. So what we know is that we have the 9H here. I think I might start with that. And that's the 3 equivalent CH3s. And I would say that that means that all 3 of those CH3s are connected to that C. So what that does is it accounts for all of those CH3s and accounts for that C as well. So you can put a little check mark on whatever you've put together first. We also have another partial structure here. We've got a CH. It's got 4 peaks, so it must be next to a CH3. I'll stop there for a second. Is anybody confused about how I know that the CH is connected to a CH3?
Can you explain it?
Okay, so the CH has 4 peaks, which means 4 peaks, that's 3 adjacent hydrogens on carbon, which means the CH must be next to a CH3. So N peaks, N minus 1 hydrogens on adjacent carbons. That's how I know. The CH3, on the other hand, has 2 peaks. So that means 1 hydrogen on adjacent carbons. So that means that that CH3 and that CH are joined together. So these 2 must be joined together. Does anybody have any questions?
I have a question.
Yeah.
On your aromatic ring, I see all the H's. What is right here?
The squiggly line,
Yes.
it's a join point because if there's only 5 hydrogens, there must be 1 place left for that to join to something.
Something. Okay. Thank you.
But it also tells you that there's only one way that we can join that ring on. It has to be just through 1 location, not through 2 on the ring.
Okay.
So what I can do is I can kind of do a little bit of trial and error here, and we can try and put the rest of this together. I can try something like this. C double bond O and the O, and then I could put the aromatic ring over here. And that might actually be close to fitting. It's actually not too bad, but it's the correct answer isn't that one, but it's pretty. It would be pretty close. Now the other thing we know is that this can't be switched around. I can't put the O. I know. Can you see my cursor?
Yes.
Okay, right. So we know that the CH is not connected to the O. because if we look at the correlation chart, we'll know that a CH connected to an oxygen is going to be at 4 ppm. Now this is fairly subtle, but it does show us something. So that's what we know from the correlation chart. You'll have the correlation chart on the test. You won't have to memorize that. So what that means is if you look at where the CH is, it's actually at about 2.4 ppm, which tells you that the CH can't be connected to an oxygen, which means that that would be incorrect. Now there's also some other subtleties that involve the aromatic ring and the shape of the aromatic ring that tell us that the O can't be directly connected to the aromatic ring and that the structure will end up being this one over here. So there's a whole lot of other stuff that goes into this, but I've sort of taught you most of the nuts and bolts of it, how to put it together. Let me show you what else you can use here to help you understand what's going on and how you can get some practice.
Is there a chart we could print out for the ppms?
Yeah, you can. It's actually, I don't have. It's kind of annoying that I can't print out this old test. Let me see if I can. Let me see. Oh, I don't have to print it out. No, hang on. Let me just open it. That's better. Okay. So if you look at any old test, you'll see there it is. So this is the correlation chart that you'll get with it. There's your proton NMR table.
Oh, good. Thank you.
And you've got also infrared, carbon-13, which we haven't looked at yet, proton NMR. Along with that, I've also got your integration chart up here, which tells you how to link the integration with the number of peaks. Sorry, how to link the integration with the number above the peaks, I mean. And then you've got multiplicity, which tells you how many peaks are equivalent to how many adjacent hydrogens, and gives you suggestions on how to interpret that as well. There's also, on this same chart, which you have access to obviously on the test, units of unsaturation. So the rules for units of unsaturation, as well as an example of how to figure out how many units or unsaturations or double bond equivalents there are in a compound. So that's stuff you already have access to. So there's your correlation chart. And I was saying earlier that a CH connected to an oxygen would be around 4 ppm. And that's how we know this, is by looking at that correlation chart. Okay, any questions?
Yeah.
Yeah.
My question is, how is this different from what we did in Orgo 1?
It isn't.
It isn't. Okay.
Not for the proton NMR, but in Orgo 1, we never went over carbon NMR either.
Okay.
But no, this is no different.
Okay.
It's just that there are a lot of people in this class who weren't in my Orgo 1 class. And some people who were in my Orgo 1 class didn't get the gist of the NMR either. But now is a chance to figure that out. So here I've got, this is on the table of contents. I've got proton NMR, the proton NMR folder. And in this folder, I've got all sorts of resources to help you practice for proton NMR. So what I did was I actually wrote this. It's a JavaScript program, And you can link to that through that folder. And there's 75 examples. I'm just going to pick one here. You got to wait a little bit for it to load up. But yeah, I wrote this in JavaScript. Give me a second, give it a second here. It takes a little while to load up. Yeah, it is super helpful. You'll see in a second. So what you'll do, and I've got a video here as well in the page here to show you how to do this, but I'll just go through this one and show you how it works out. So the first thing is you look at the molecular formula. So C equals 10, H equals 15, N equals 1. So it'd be C10H14, which would be C10H22, which means it should be 4 double bond equivalents. I'm going to put in 5 and I'll show you what happens. It says the double bond equivalents are incorrect, but you can change it. 4 is correct. And then see, it says DBE correct. To continue, select the pieces below. Watch as the molecular formula counts down. So what's going to happen is I'm going to pick the pieces as I see them here. And then what I want you to do is watch as this counts down. So you've got C10H15 right now. 5H in the aromatic region, that's a C6H5. That would be this piece here. So I click on this piece and you see it appears over, should appear over here at some point. Let me make this so it takes up less of the screen. There we go. But look what happened. You see, when I selected that piece, it actually counted down and took that piece out of the molecular formula. So it took C6H5 out. Now the 2H, now the BR here means broad, not bromine, and it indicates that it's most likely an NH2 rather than a CH2 because it is a single peak as well. And often those OHs and NH2s tend to be broad, so that's an indication that's likely an NH2. So I'm going to select that piece, NH2. But again, you'll notice that it counts down, takes the N out, and then 2 hydrogens. And then what's left, we've got a CH, so I'll get a CH here. And there's 2 CH2s, so I'll take out those. And a CH3. You'll notice that there's nothing left. Okay, sometimes there's stuff left, but then you can figure out what would be left over. It might be a C, an O, and a double bond. I was kind of hoping something would be left over, but there wasn't anything left over. Yeah, it's excellent for practice. Victoria's right about that. So once this is counted down to 0 and you've picked all the pieces, you can check the pieces and make sure that they're correct. It turns out they were. And then what you can do is you can actually put it together. So the anchor goes on the anchor, and then you can put the rest of it together. But you've got to put the rest of it together in such a way that it makes sense. So I could try this. I can put the CH down here. I can maybe put the CH2 over here. And then I can put the CH2 over here. I could just try this and see if it works or not. And then I can put the CH3 up here. And I can put the NH2 down here. And then I can try to submit the structure. And it says it's incorrect. So it means I have to move the pieces around. So I should be trying to look at this and be able to determine that. And what I should do is realize that this CH has 5 adjacent hydrogens, because you can see it's got 6 peaks. If you look up there, it's got 6 peaks, so 5 adjacent hydrogens, which means it's more likely like this. And when I submit it, It's still incorrect. So I must be still doing something wrong. So the CH must be in a different location. Sorry, this is going really slow for some reason. Okay, so I could try that, see if that works. There you go, it says it's correct. And then after it's correct, let's say you got it just by trial and error, just like I did just now. You can click on this link here and it goes to a video that tells you exactly how the structure was obtained. I know you can't hear it.
Thank you. Thank you.
Okay. But there you go. So that's there's 75 of those examples, and they all have videos attached to them as well. And you know you can go through. There's also a PDF file with all the answers as well as the assigned spectra. So with the A's, B's, and C's and everything else on it as well. So let me open that.
Found this very helpful.
Yeah, it's pretty decent if I do say so myself. It's unique. I don't think anybody's ever done it before. But you can see how I've got this labeled here with the letters and stuff. That's to help you figure out the labeling. So it's all there too. And the other thing I have, okay, there's a video on how to use the tool. So if you didn't catch something that I talked about just now, you can always watch that video. And I've also got this NMR guide as well, which I've got in the folder on my courses too, which has the charts and also gives some information about how to figure out what's attached to an aromatic ring with regard to peak shapes and what to do if you've got a 6H peak, whether you've got 2 CH3s or 3 CH2s. So I think that's worth a read as well. So all of these resources are in this folder, this Proton NMR exercises and answers. And I really feel like the best way for you to practice this is to go in and use that tool. So you've got the directions on how to use it. You've got the video solutions, all 75 video solutions are here as well. You've got the answers to the NMR exercises, the ones I just pulled up. And the other thing I have is this index of functional groups and exercise examples, where I've gone through and said what examples belong to what functional groups. That could be handy for later. It's not so much useful for right now for you, but it's useful for later. And then you've got the link here to the NMR tool, which is on my website. All right. Does anybody have any questions? We haven't been through everything yet. Remember, the question that's on the test has proton NMR and carbon NMR as well as IR. We don't need that. It looks like I've lost my link here. Okay. So it's going to be all about practice for you all. And watching some of those videos, video solutions. I think once you do that a few times, you'll get a much better idea of what you need to do. You're welcome, Donna. It was a lot of effort, believe me. I had to learn
I can
JavaScript.
imagine.
I had to learn JavaScript from
Oh my
scratch to
Oh,
do it.
geez.
Yeah, I did it in Flash originally, which I had to learn from scratch, and then Flash went away last year, so I had to rewrite it in JavaScript. Okay, so we're going to now start looking at carbon-13 NMR spectroscopy. And what we're going to find for carbon-13 is that it's similar to proton NMR, except now we're looking, instead of protons, we're looking at carbon-13. Now, carbon has two isotopes that we talk about, main isotopes, carbon-12 and carbon-13. Now, carbon-12 takes up about 98.9%, and carbon-13 is about 1.1% of all natural carbon. So this allows us to be able to actually see carbon-12 doesn't have a spin associated with it, a magnetic spin. Protons do, but carbon-13 does. Carbon-12 doesn't. Carbon-13 does, and that allows us to see it in NMR spectra. And you can look at the correlation chart here, and you can see that I've circled certain Cs, and this is where you expect them to appear on the the carbon NMR spectrum. And you'll notice a couple of things. The carbon NMR goes from 0 to 200, whereas the proton NMR went from 0 to 10. But you'll notice that these carbons appear in similar locations to where you'd expect hydrogens in similar environments to appear. So, you know, a hydrogen will appear between 7 and 8, which means you'd expect it to appear about between 140 and 160, which is what it does here for a carbon. Now, the same thing applies to carbon-13 as applied to protons when we're talking about symmetry. So in this instance, we label everything, including, well, we're labeling all the C's here. In the previous thing we were doing with the proton NMR, just to compare it, I had this as an example, I think, in the proton. No, it's not the same thing, but it's close enough. And all I had labeled was A, B, C, and D. I never labeled this. And that was because we were only labeling hydrogens. See, now we're labeling carbons. And you can see we're seeing the same kinds of patterns here with symmetry. So if I labeled this one, I'd expect it to have 6 peaks, A, B, C, D, E, F, but I labeled this one as well because it's a carbon atom. And this one would be 4 peaks, A, B, C, D. This one would be 3 peaks, A, B, C. And this one's A, B, C, D, E, F. So that would be 6 peaks as well. But notice the symmetry here, how we can do D, D, E, E, and F, F because of the line of symmetry that's down the center. Does anybody have any questions about this so far? So this is an example of what a carbon-13 spectrum looks like. And you'll notice it consists of a whole bunch of single peaks here. But I do have some labels above these peaks. Let me see if I can enlarge this a bit. There you go. I'll move this around a little bit. Okay. So you see all these single peaks here, but they have letters above them. Now these letters, I'll get to them in a minute, but the letters give you an idea of how many hydrogens are connected to each of these carbon atoms. You'll also notice this one's not labeled, the one around the 120. That's because it's been zoomed in on here. So this area here, it has these 3 peaks that I'm circling, is this area here, just zoomed, so you can see it a bit more clearly. So what looks like a single peak is actually 2 peaks, but they're very close together. So these letters here tell us how many hydrogens are going to be attached to each of these. And that's due to a different kind of spectrum that we're taking with the carbon that allows us to determine that. So it's really kind of like two carbon spectra in one. But the letter codes are as follows. Q is a quartet, and that's 4 peaks, which would be a CH3. T is called a triplet, that's 3 peaks, and that's a CH2. D is doublet, that's 2 peaks, that would be a CH. And S is a single peak, 1 peak, which is a C without any hydrogens on it. So that enables me to look at each of these peaks and be able to tell what kind of carbon we're dealing with, how many hydrogens are attached to it. So if you look at H, which is a CH3, that's why that's a Q. These guys here, E, F, and G, are all triplets or triple peaks with the T here. So those are all CH2s. D is a single peak. That's this one down here. It has no hydrogens on it. And A, B, and C each have 1 hydrogen, which is why they're all Ds. You don't have to memorize that because it's actually on the chart that you get with the test. So I'll just pull that up again. Here it is. So you've got the carbon NMR table here, which tells you where you can expect to find these different carbons, where they're going to be on the spectrum. The other thing that's important here is the multiplicities. Q is a CH3, T is a CH2, D is a CH, and S is a C. So that's all there for you. You don't have to memorize any of that. But because carbon-13 only makes up 1.1% of all carbon, it's going to be very unlikely you'll see one carbon-13 next to another carbon-13. The probability would be 1 in 10,000, which is why these are always going to come up as single peaks. They're not going to be coupled. The Qs, Ts, Ds, and Ss, we use a different kind of spectrum to show that, and that's the coupling of the C13 to adjacent hydrogen atoms or hydrogens attached to those carbon-13s. And that's allowing you to tell that. Does anybody have any questions? The CdCl3 here is a solvent, so you don't worry about that. Any questions? All right, let me show you what you'll be dealing with on a test with regard to this. It's actually not too bad. So what I'm going to show you on the test, you'll have a few more to deal with. It might be 4 or possibly 5 compounds you'll have to look at, but it's a matching exercise. So the idea is that you'll have the carbon spectra, and then you'll have the compounds that they could be as well. And one spectrum will correspond to one compound. So let's look at how we would solve something like this one here. So the first thing you would do, and it's the first thing I would do, is I'd look at each compound and see how many peaks I expected to see. So you see this has already been numbered, and this is just so it will help with the numbering later, but all the carbons have been numbered. And this doesn't account for symmetry, by the way, but this one would be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So they all should have 4 peaks, which is the first thing you should look at. And the next thing you should look at is to be able to figure out which one is which based on how many Q's, D's, T's, and S's there are. So for something like this, you can see that for the first one, the one with the OH on it, that would have a Q and 3 T's. Does anybody have any questions about how I know this? That this is going to have a Q and 3 T's? Any questions?
Yeah, how do you know it?
Because that's a CH3 and these are 3 CH2s. So I'll just, remember you have access to this, you don't have to memorize it. So I know that this one would be Q, T, T, T. Same with the NH2 compound as well. That's going to be Q, T, T, T. Are you okay with that, Julie?
Yes.
Okay, now the other one would be 2 Qs, a T, and an S. I'll write them on here. Q, T, Q, and S. And you can see which one that would be from here because these two here have 1 Q and 3 T's. This one has 2 Qs, a T, and an S, so that must be the one I'm pointing at here. Does anybody have any questions so far? All right, what about the differentiation of these two? Well, now we have to use a chemical shift to look at that. Now, if we look at the chemical shift, I think I've got that on the next page here. Focus on the peak that's furthest to the left because that's going to be closest to the electronegative group, which is the oxygen. So we're really focusing on these carbons here. And this one should be at around 60. And this one will be at around 40. Okay, so how do you know that? Well, let's go back to the correlation chart and take a look at it. And you can see here that C's connected to O's are around 60. C's connected to N's are a bit lower, sorry, a higher field, upfield from there. So those are around 40. So CN's around 40, CO's around 60. So based on that, then you can distinguish between those two. You can distinguish between these two spectra. And again, you're focusing on the one that's furthest to the left because that's going to be closest to the electronegative group, be it O or N. This one's around, I guess it's around 68. This one here is at around 50. So it enables you to tell which is which. Does anybody have any questions? So that's what you'll be looking at on the test as well. Let's see, I'll show you a test question here so you can see it, and I'll go through it.
The ones that's further is the one that is,
The one that furthest to the left is closest to the electronegative group.
okay.
You'll see, you'll get the hang of that. And that's why I was focused on those specific ones. These ones here connected to the O's. Then you'll see, you would have seen a progression. Let's see if I can show the progression here. See, the further things are away from oxygens and nitrogens, the more to the right they appear. So do you see the Q here, and this T, and this T, and this T? So the numbering See, I might have a number in on the next one. Yeah, I do. So this is carbon 1. That'd be 2, 3, 4. See the progression as we get further away from the nitrogen?
Yeah.
So the ones that are closest to the nitrogen and oxygens are closer to the left. And that's really handy to know. Is that okay?
Yes. Thank you.
All right, so here's our compounds here. Let's see how many are there. There are 4 here. All right, so what I want you to do is look at these compounds I have down the bottom, and I want you to be able to look at them and be able to tell me how many peaks you expect to see for each of them. Now I'm going to tell you that the numbering I've got here does not reflect symmetry. Okay, so it doesn't reflect symmetry. How many peaks do you expect the first one to have, the one furthest to the left?
Can I ask you a question?
Yes, Julie.
When you say it doesn't reflect symmetry, I don't know what that means because
You will in a second. So just wait a second, okay? It'll become clear in a second. How many peaks do you expect the first one to have?
6.
6. It would be 6. Now, I did hear someone say 4, but there's no symmetry here. These are all different. Every carbon here is different. There's no line of symmetry at all in this compound. So that would have 6 different carbon peaks. Now, Julie, this will explain what I was talking about earlier. How many peaks will this one have?
2.
How many?
2.
2. And the reason for that is because there's a plane of symmetry down the center of this compound. Right here. So 1, 2, and 3, and 4. But 1 and 4 are the same, and 2 and 3 are the same. So what I'm saying is if I had numbers that were reflecting symmetry, then it would have been 1, 2, 2, 1. That's what I would have written, Julie.
okay, thanks.
Now, if you look at this one here, how many peaks do you expect to see for this one?
4.
Not 4, 3. The reason is because these two are the same. They're related by symmetry, right down the center. So that would have 3 peaks. Is everybody okay with that?
Can you draw? Where are
Sure,
you drawing the line of symmetry?
sure.
Thank you.
Do you see that? So if I was labeling for symmetry, I would label it 1, 2, 3, 3. The reason I haven't here is because I don't want to give away the symmetry by numbering it the same.
Right.
It makes it a bit too easy, I think. How many peaks would this one have here?
2.
2, because there's a plane of symmetry down the middle here. So that tells us that the one with 3 peaks, there's only one that has 3 peaks. Let's see if we can find it. There he is. Is he? Hang on. There he is, right here. This is the one that has 3 peaks. That must be this one. And I'd expect it to be, that is a Q, that's a T, and this is a Q. So 2 Qs and a T. And what do you know? 2 Qs and a T. So that must be the right answer for that one. Anybody have any questions so far? So both of these have 2, and this one has 6, and so does this one here. 1, 2, 3, 4, 5, 6. And I'd expect 3 Qs and 3 Ts, and that's what I see. Q, 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 and 3 Ts. So that's okay. Does anybody have any questions so far? All right, so if you look at these other 2, I know I can't really, let's see if I can extend this out a little bit. Yeah. You can look at the T, which is the CH2, and you can see where it's located. This one's at around 60, and this one here is at around 40. And you'll notice that this one has a CH2 on the O, that would be around 60. And the one CH2 would be around, on the end would be around 40. So that's how you would distinguish between those two. This would be the one connected to the O, that's around 60. And this would be the one connected to the N, it's around 40. So that's how you'd be able to tell. And then I would expect you also to be able to number the peaks as well. And you can use that guideline I told you earlier. The closer the carbon is to an electronegative group, the more to the left the peak will appear. So I would expect 2 to be more to the left than 1, for example. All right, does anybody have any questions? So in the blue book, let me expand out from here. I do have some more resources here. I don't actually have a tool for the carbon-13 NMR, unfortunately. One of these days I might write one, but I haven't done that yet. The proton NMR is, if you know the proton and understand the proton, the carbon's pretty easy, I think. All right, let's look at the blue book here. So test 1 problems.
Excuse me, Professor.
Yeah,
You had said something just a second ago. You said the closer the carbon is to the electronegative group,
the more to the left the peak will appear, yeah.
more.
And let me see. So starting on page 46, I've got these 2 matching exercises. They're like 8 or 10 though, 8 or 10 carbon spectra. There's answers here to these as well. But I'd recommend doing that. That's a really good exercise, really good practice. So you got the spectra, then you got the compounds after it, and I've got 2 of those. So those are really good. And I think if you do those and you look at the ones on the old test, I think you'll be okay. People usually don't do badly on that question at all on the test. It's really not too bad. It's not too hard. Now we're also dealing with it in lab as well. So on next Thursday, you'll see all this too. Okay, does anybody have any questions?
Yes, looking in the blue book, I'm sorry, just before you get off of that.
Yeah.
So I'm looking at those pages where it gets to the 45 and 46.
Yeah.
And I'm just curious, like when I see the graphs, I kind of know what you want, but when I see a box that has a whole bunch of compounds in it, how are we supposed to link those? I think you need to go up, scroll up
Okay.
just
Okay.
a smidge, couple
Well,
pages.
Okay. So it starts out. I know it does lack it does lack directions here. Don't worry about those
Yeah.
boxes. No. These are the spectra.
Okay, yeah.
And then after that, you've got the compounds.
Okay, so what are those boxes up there? What would we have to do with those on
That's
the
for
test?
that was actually for the IR.
Oh, I understand. Okay.
And these are the spectra that correspond. Sorry, these are compounds that correspond to those carbon spectra.
Okay. Okay, and so those boxes that have multiple things in there, you're supposed to select which one of those options for that number 1 is.
Well, that's a bit more complicated, but yes, that was
Okay.
for the IR.
Okay. All right, thank you.
All right, no worries. I need to plug in my computer. Give me a second, please.
You go.
going to run out of battery if I didn't do that. Okay. Any other questions so far about this? I was going to go through another couple of examples.
I have one more question about the proton NMR. Is that okay?
Yeah, sure, yeah.
I forgot. I remember there was a difference between if it was 6H, whether it was 2 CH2s or 2 CH3s.
Mm,
What
okay.
told the difference again?
Okay. I'll show you the document where we can go through that, and I'll be very specific about it.
Okay. I was looking for it this entire time and I couldn't find it.
Okay, so it's in the Proton NMR folder, and we're
Okay.
looking at this. If I can find it here. Huh. I thought I had it in here. I guess I didn't. All right. That explains that, Julie.
Yes.
All right, but I will definitely.
It is in there. Look.
It is?
Yeah. You talking about this one right here? I don't know if you can see it on my screen.
Hang on. Let me see. I'd have to. Hang on. Okay, somebody's holding something up.
It's me, Deanna.
Okay, I can't see anything. Sorry.
But it is in there.
It is in here. Okay.
I just printed it.
You just printed it. Okay. This one here. Oh yeah, NMR guide. There we go. Yeah, here it is. Yeah, so yeah, NMR guide and the answers. Okay. So it's in here, Julie. 6H, 2 CH3s or 3 CH2s. So it's under NMR guide and answers to NMR question exercises. And I would say that in 99% of cases, if it's 1 peak, 2 peaks, or 3 peaks, it's going to be 2 CH3s. And if it's 4 peaks, it's going to be 3 CH2s. Is that okay? Julie?
Sorry, I'm nodding and I'm on mute. Yes, thank you.
Okay, cool. All right. Does anybody have any other questions? Okay, I have to shrink this screen a bit here, make it a bit easier for me. All right. Let's go through another example. There we go. See if we can see them all on the screen here. There we go. All right. So let's take a look at, first of all, how many we expect to see for each one. So looking at the one on the far left, how many carbon peaks do you expect to see there?
4.
4 is correct because they're all different. What about this one here, the one next to it?
4.
4. And the one next to that?
4.
And the one next to that?
4.
4.
So they all have 4. All right. So this one here, can anybody tell me how many Q's, T's, D's, or S's we expect to see for this one? Let's see if I've got it still here on my paint. Here we go.
2Q, 2T.
Yeah, 2 Q's and 2 T's on the first one. What about on the next one?
2Q, 1T, 1 D.
No, it's an S.
S.
Yeah. 2 Qs, 1 T, and an S, because that doesn't have any hydrogens on it.
Oh, all right. right.
That's good though. I appreciate you trying on that. That was good.
Okay.
So is everybody okay with that? 2 Qs, a T, and an S? Anybody have any questions? Okay, what about the one next to it?
2 Qs, 2 Ts.
2 Qs and 2 Ts. And what about the one next to that? This one here at the end.
2 Qs and 2 Ts.
That's 2 Qs and 2 Ts as well. So you can see if we can use that to distinguish between them.
What was
And
the first one again? Because,
2 Qs, a T, and an S.
okay,
Did I say something different? I might have. I might have.
think.
Yeah, I might have. That's possible. I might have said it was a D when anyway, it's 2 Qs, a T, and an S, definitely. Same with this one. They're both, so these two are the same and these two are the same, at least for the Qs and Ts. But you can see this has 2 Qs, a T, and an S. This one has 2 Qs and 2 Ts. This one has 2 Qs and 2 Ts. And this one has 2 Qs, a T, and an S. The focus would be for these two on carbon 3, the one next to the nitrogen, the one next to the oxygen. So I'd expect carbon 3 in the case of the oxygen to be at around 60 ppm and the one for the nitrogen to be around 40 ppm. So you can see this one has a T at around 60 and this one has a T, sorry, this one's a T around 40. This one has a T around 60. The one at the top has a T at 60. So I would make that one the oxygen one. And this one, which has a T around 40, would be the one with the nitrogen on it. Then you could focus again on the carbon 3 for nitrogen and oxygen down here as well. That'll be helpful. And you can see actually the Q and the T are very close together because they're next to nitrogen and oxygen respectively. This one is around 60, this one's around 40. So this one's next to the O and this one's next to the N. So that's kind of what you'll be doing in each of these. It's really not that bad. Once you have some practice at it, I think you'll be okay with it. Does anybody have any questions?
Just to make sure I understand it correctly, since oxygen is more electronegative, the carbon that is next for the first two, comparing the first two, the oxygen that the carbon 3 next to the oxygen would be in the 60s.
Yes.
And the one next to the nitrogen would be 40.
Yeah, that's right. According to the correlation chart. Yeah.
Okay, thank you.
All right. Well, that's it for today, folks. So I'll see you all on Tuesday. If anybody wants to hang around and ask me any questions, they're more than welcome to.
Thank you.
Thank you.
Thank you.
All right. Have a good day, folks.
Thank
You too.
Thanks. Have a good one.
So I had a question about lab.
Who's this, Mary?
Yes.
Yes.
So I think someone was gonna ask in the deadline, like in the assignment, it says something about the first lab assignment due Thursday, 9:30 a.m. But I know that you mentioned that there's nothing due before lab starts.
Yeah, not for us because the first 3 labs are dry labs. There's no procedures due. The first one you'll have to do will be for February 11th.
Let me look at it and tell you.
What she's saying is the Dropbox says that it's due at 9:30. The time that class starts is not due at the end of class.
That's
She's
true.
right.
No, she's right. Yeah, you're right about that. I wanted it due before class starts. Yeah. Is that what it says in the syllabus? It should say before class starts.
For the dry lab, I thought you wanted them due at the
But
end
dry,
of
no,
class.
no, but it's your dry labs. Those aren't procedures. Those would be actual. No, dry labs are due at the end of lab. But
Right,
that's not a procedure.
that's what she's saying. In the Dropbox for the dry lab itself, it's saying that it's due at the beginning of class.
Oh, it is.
Yeah.
It's
okay. Well, that's a problem.
Okay.
That's a problem. Those
Yeah.
should be due at the end of class, and that's my mistake for setting them up wrong.
Can I ask another question?
Yeah.
Oh, that's a different person. I'm sorry. But I also have a different question, but it's about aromatic quiz for the lecture that relates to test 1. It doesn't have a due date. Does it mean that it's due still before the test 1 begins?
Yeah, it would be. It'd be due the day before.
I mean, it makes sense. I just wanted to clarify. It makes sense if it's before the test 1.
It will, but now there's a see, with that one, what happens is it opens up something else, and that's what's going to be due, and that's things worth points. So that one actually isn't worth points. It opens up something that is worth points.
Okay, but I just want to make sure that it's.
But
I wanted to know when to take it. Is it covered within the test 1 material? So I should wait until we.
I
get
think you
to
should wait.
aromatic?
I would wait if I were you.
Okay, there you go. That's what I wanted to know.
Yeah. Let me take a look at this Dropbox here. It's what you're talking about. Yeah, that should be 1210. Yeah. All right. Yeah, I'll fix those. All right. Is there anything else anybody has questions about?
Yes, I had a question about when you were going over the test, Dr. Musgrave. Number
Mhm.
3 gives those 3 graphs, like the IR, the carbon-13, and the proton.
Mm-hmm.
Can't we solve that without using anything but the proton?
Yeah, you could. I mean, they're all just there for you to do what you need to do.
Okay, like you could technically use any and get the same answer in a way.
Yeah, or yeah, they're all supposed to correspond to the same thing. Yeah.
Okay, that makes sense.
Thank you so much. Have a nice day.
Okay, no worries. I'll see you later.
See ya.
That one will make it. Okay.
Also,
Yeah.
how do you think, like, me and Keisha, that's funny. Anyways, for this, like, just keep studying how we were in Orgo 1.
Yeah.
Doing
Yeah.
the
Study
same
those
thing.
mechanisms and do any problems and anything else I
Okay.
assign to you, and I think you'll be all right.
Okay, next week we're gonna start mechanisms, correct?
Next week, yeah,
Right.
we'll be starting on some aromaticity. It's more like theory, really, and
Okay.
then we'll do some. Then we'll get into some reactions after that.
Okay, so basically just keep up with like what you give us each class day.
That's
and,
right.
like, okay, because I don't know, this stuff looks harder than last year. Like, I don't know why, but it looks more daunting.
Oh, it is.
I don't know. Like, I don't know how to approach it.
Well, it's organic too here. You know,
It's true.
this isn't kindergarten anymore.
Yeah, it was never kindergarten.
I swear. I don't know. What's the hardest test this semester? Because last semester it was test 3, but what would you say?
Test 1.
Oh, really?
Yeah.
That's good.
Yeah, you get
That's
the
really
hard
good.
stuff out of the way first. Yeah.
Yeah, that's good.
You know
We
what the
can get it
easiest one
done.
is? Test 2. Test 2 is easy. Test 2
Oh,
is super
really?
easy. Yeah.
That's
Oh, that's
good. I
Test
like
3 is sort of in between test 2 and test 1, and test 4 is kind of between test 2 and test 3.
that. So that means test 4 will be pretty easy too.
Yeah.
Yeah.
Yeah, it's
That's
a
good.
little bit more difficult than test 2, but not too much more.
What makes test 1 so hard? Like, is it
Because there's so many different things that we do. It's
Okay.
all, there's a whole potpourri in here.
okay?
Not just sort of one thing.
Yeah.
We're doing a lot of different things.
Okay, that's what I
Yeah,
noticed, because that's why.
We're doing NMR and IR, then we're doing acidity and basicity, and we're doing
Yeah.
carbon-13, proton. You know, it's just
It's just like a bunch
Looks
of different stuff.
crazy.
yeah,
Yes.
it's a hodgepodge.
Yeah, it does look pretty crazy there, Musgrave.
Yeah, that's right.
But I feel like, I don't know, like I was trying to work ahead and like study like early, you know what I mean? But some of this stuff, like I feel like I really need to wait till your lectures. 'cause
No, I think it's a
don't
good
know.
idea.
Yeah,
I think
yeah,
for a lot of that,
exactly.
I wouldn't work too far ahead. I think you could
Exactly.
get yourself pretty lost.
Yeah,
Lost in
I did. And I was like, maybe not. This isn't a good idea.
Yeah, there's better ways to use your time.
Yeah, like the procedures. Yeah. Do all the procedures.
Yeah.
Yep. Pretty much. That's how I use my time.
Yeah, I think it's a good plan. I like it.
Yeah. Yeah. I don't know. Do you think working ahead on labs is bad? Like kind of how we did
No,
last year?
it's fine. Like I said, I'll get together the data sheets and stuff this afternoon.
Thank
Okay.
you.
All right.
Okay. Yeah. Because we're already starting like some research, but I didn't know if it was like bad to do that.
No, it's fine. I'm going to do some. I'll put the data sheets together, and you'll have it all ready to go.
Also, for the spectral quizzes, like, will they all pretty much be the same and we base it off the nitration of methyl benzoate?
Yeah, that's going to be very similar to that. If you can do if you can do that one, then you can do them all. Is what I'm saying.
Okay.
Okay, yeah, we were just figuring that out between lab and lecture today. And it's
No,
not hard
did you
at
look
all.
at the video?
Yes,
Yeah.
it was pretty clear after that.
Yeah, and then you got the practice quiz you can do, which is actually the very first quiz too. So there's no reason anybody should be getting any less than 100% on the first quiz.
Oh, it's like
It's
parallel?
the same.
It's the same.
Oh, wow.
Oh.
Like same exact questions and everything?
Yes.
Oh my gosh.
Is
That's
there a
crazy.
reason why the other spectral quizzes don't have a practice, or?
Because they're all based off the same thing.
Oh, okay.
I mean, if you can do that, what I'm saying is if you can do that one, you can do them all.
Oh.
Okay, and then how would you find like what you start with, like how we use the methyl benzoate to do the like cuts at the C to O,
structure.
C to C, yeah, the structure.
Well, we haven't gone through mass spec yet, but we'll do that. We'll do that in the third week.
That's just like the cutting of it and
Yeah,
counting up
that's
like
right.
the masses, correct?
Yeah, that's right.
Okay. Oh, mass. Oh, that makes sense.
Yeah, that question's gonna be.
I didn't even think of that before.
That question's gonna be in all of the spec quizzes.
Mm-hmm.
Okay.
Yeah.
So we could figure out the structure. We technically could do all the quizzes ahead of time.
Yes.
We want to be crazy.
Yes.
Okay.
Oh,
Absolutely.
wow. Like
Yeah.
legit, we could work it out in a way.
Yeah.
We could just work out all of the different
Sure.
structures.
Yeah. Well, no, you've
And
got
then
all the
it'd be the
structures
same.
there. No, these are just assigning spectra. So all the structures are already there. You just have to assign them.
Okay.
Okay.
And it gives you the numbers, if I'm not
It
mistaken, right?
does.
Like
Yeah.
okay, the ones you got to show like what's on each side.
Yes. Yes.
Yeah. Okay. That's pretty easy, actually.
It's
I was
not
actually scared for those. Like,
Well, I don't think you need to be that scared.
yeah. Well, it was just because I didn't know what it was. Like, I've never seen a spectral
Yeah.
quiz before.
Of course.
Yeah.
After watching that video, that was the hardest question of the quiz. Was
Yeah.
that one.
Yeah.
Also for lab, the QA thing, I was trying to figure out what are all the groups and stuff like that.
Oh, I'm going to assign groups to you,
Mm-hmm.
but later.
And then we're all gonna have like, I noticed like the lab portion, like the post conclusion stuff is only like 30 points or something. And there's like 2 different quizzes that are 30 points too. Like, is it basically all quizzes and pre-lab, I think was 10 or something?
Yeah. I think there's the only written portion is like 40. I think it's 40 points is for the
Okay.
QA
And
report.
is that hard? Because that was
No, because it's all based on it's not.
Okay. Perfect.
That's one I definitely don't want you to work ahead on because
Yeah.
I need to give you more information about that and how to do it. It's very specialized.
Yeah, we definitely saw that. That one gave me a headache, and I was like, "Yeah, no, I'm not looking at this one."
No, leave that.
Yeah,
leave it be. Leave it go.
Yeah, definitely. And that's a dry lab anyway, so we'll have to come to class anyway. So.
Well, no, and actually, not necessarily, but it's. I tell you what, it's going to be harder, very much harder, not coming to class than coming to class.
Yeah, I feel like you go over the answers anyways as we do it in class.
I
too,
do,
like-
and I will.
Yeah. No.
Yeah.
Yeah. Even like from the pre-lab and stuff, are you gonna go over some like of that too? Like
Well,
of
not not really, because that's all. The pre-lab is actually something you should be able to figure out from the lab itself.
Okay. Oh, like the lab book, like how
Yes.
Gen Chem used to be?
Yes.
Okay. Oh, that's good. It's really good. I don't know. I just want to like work ahead. Like I feel like the semester's already like halfway done in my head, and I just want to be there. I don't know if that makes sense. But
Yeah, it does.
yeah, the last semester of chemistry, you know.
That's right.
Yes.
That's right. It's a bit sad, but you know, you'll get
It
through
is.
it.
It's like sad, but it's happy. I don't know. I don't know what emotion to be on.
I'm happy to be done, but we're definitely gonna miss you.
Yeah.
Oh, you won't miss me.
It's been a lot of years with
Yeah.
Musgrave.
No, but you won't miss me. It'll be fine.
Oh, we will.
You'll be
Oh,
fine.
yeah.
You'll be fine.
When are you retiring, Musgrave? I remember you talking about that a couple of years ago.
58. Oh, sorry. 7. Now you're finding how old I am. 7 years.
7 years?
Mm.
That's a lot of years.
Yeah.
Huh?
Crazy.
That's right. You guys will have been married with kids by then.
I'm
I don't know
already
about that.
married.
Only
Oh, you're already married.
26.
Okay. That's right. Yeah, Keisha's already married.
Yeah, I'm
What-
just
what-
a little young.
Yeah.
I'll be
yeah.
26 then.
Yeah, well, who knows? Who
Look
knows?
at
We'll give you references
Oh
Yeah,
yeah.
for all the students too.
that's right. That's
We
right.
have some students don't like you, Musgrave, though, gotta say. Some
They
are like
don't?
scared of you.
Yeah,
Yeah.
that's all right. They can be as scared as they like. I don't care.
No, I know. I'm like, you guys are missing out.
Right.
Yeah,
Sure.
well, you know, it's part of you just have to figure out that it's not as scary as it seems. You know,
That's true.
neither am
And
I.
also like, I don't know, you're just so direct, but like I like that, but other people don't. Like
No,
people
they
like
don't.
to fluff it out.
Yeah, no, they want yeah, I'm real direct. Yes, I will.
Yeah. But like I'd rather have
I'll
that
say it.
than
Yeah, I'll say it like it is. And
Yeah.
that's where I come across as being condescending and cold. If you look at
yeah. Yeah. I'm sure a lot of people see it that way as well.
that's right. All right,
Well, that's it. We just need to start preparing, I guess, Keisha.
that's right. That's right.
All right. Well,
right, thank
see you
you.
next week.
No worries. I'll see you guys later. Take it
Bye, have a
easy.
good day.
Bye.
Bye.